Alright, so the question that we're going to solve today says, a model rocket is launched from rest with an upward acceleration of 6 meters per second squared, and due to a strong wind, a horizontal acceleration of 1.5 meters per second squared. How far is the rocket from the launch pad 6 seconds later when the rocket engine runs out of fuel? So I began by identifying two variables that we know already. One of them is the vertical acceleration, which I have written as a sub y equals 6 meters per second squared. And just to help visualize it, I'm going to write that this is the vertical acceleration. And here we have a sub x equals 1.5 meters per second squared, and that is the horizontal acceleration of the rocket. All right. Another thing that helps visualize the problem is if you draw a little graph of the trajectory of this rocket. So I'm going to draw the rocket's path on this graph. It starts out from rest at some random origin, which I've written as 0, 0. And since it has vertical and horizontal acceleration, it's going to be moving up and to the side. So the path that I'll draw the rocket will probably look something like that. And I'll denote this as r. Now to find the total distance that this rocket traveled, we can add up the two components that it has. It has an x component, this a sub x, which is this length right here. And then it also has a vertical component, the a sub y, which is this length right here. So in order to find this length r, we have to add the components r sub y and r sub x. In order to do this, we can use the equation x is equal to x naught plus v naught x plus, v naught x times t plus 1/2 the acceleration of x times time squared. There are a few variables that we already know. Since we know that the rocket started from rest, its initial position, x naught, is equal to 0 meters. The initial velocity in the x direction is also 0 meters per second. We know that the acceleration in the x direction is 1.5 meters per second squared, and that the time is 6 seconds. The only variable right here that we don't know is the position, x1, after 6 seconds. And that's what we'll be solving for. So using this equation, we'll plug these values in. x1 is equal to, this x naught is equal to 0, so we won't include that. Similarly with v naught sub x is equal to 0. So x is equal to 1/2 times 1.5 meters per second squared times 6 seconds squared. When you simplify this, you'll see that the seconds per squared and the acceleration and the time cancel out, and this will leave you with a value of 27 meters. That's the total distance that the rocket traveled in the x direction. Now we have to find the distance that it traveled in the y direction. And we can do this using the same equation, only I'm going to replace the x's with y's. So we'll have y1 is equal to y naught plus v naught sub y times time plus 1/2 the acceleration in the y direction times time squared. And we'll use the same assumptions that we used in solving for the x component, and that's that y naught is equal to 0 because the rocket started from rest. Similarly with the velocity, you started from rest, so your initial velocity is 0 meters per second. I'll write meters here just so we can keep track of the units of measurement. time is again going to be 6 seconds. And we're solving for y1, or the final position in the y direction. So we'll plug these values in again, and we'll see y naught is equal to 0. V naught sub y is also equal to 0. So y is equal to 1/2 times the acceleration of a sub y times time squared. So we'll plug that in, we get y equals 1/2 times, and oh, I forgot to write right here the acceleration in the y direction again, just to keep track of that variable. So the acceleration in the y direction is again 6 meters per second squared. We'll plug that in here. Oops, sorry, squared. Times 6 seconds squared. Once again, you'll see that the seconds per squared and the meters per second from acceleration and the second squared from the time are going to cancel, and that'll leave us with a unit of meters. So and let's see, let me plug this into the calculator real quick just to check that math. Should equal 108 meters. All right, so now that we know the x and y components of this rocket's trajectory, we can find this length right here, r, by adding the x and y components. And we can find that using the Pythagorean theorem, a squared plus b squared equals c squared. Because we know that a, in this instance, I'll say that a is r sub x, and b is r sub y. So r sub x squared plus r sub y squared equals r squared. We can solve for r by taking the square root of those values. So we'll just plug in the values that we found for r sub y and r sub x. R sub x is equal to 27 meters, and r sub y is equal to 108 meters. So in order to find r, we'll take the square root of 27 squared plus 108 squared. And let's see what that is. Plug that into my calculator real quick. That's equal to 111.3 meters. That's the total distance that the rocket traveled after 6 seconds.